Hi everyone. So today we're looking at determining the nitrate and nitrite content in samples. So we're going to start with nitrites, and the nitrite determination is a two-step process. So we have two reagents, sulfanilamide and NED. So the first reaction is with sulfanilamide, and that produces a diazonium compound when it reacts with the nitrites. And then the second part, we add the NED reagent, which is naphthyl ethyl diamine dihydrochloride, which is a mouthful, which is why we like to call it NED. When it reacts with the NED, then it forms a colored azodye compound, which we can measure on the spectrophotometer. So we're going to start with our calibration curve, and then we'll move on to measuring some samples. So we have a variety of samples here from 0.01 ppm all the way up to 0.2 ppm that we're going to use for our calibration curve. So we're going to start with the lowest, with the 0.01 ppm, and I already have 50 milliliters of that standard measured out in this Erlenmeyer flask here. So the first step is to add the sulfanilamide, okay, right here. And we're going to add 1 milliliter using a Eppendorf pipette. So just 1 milliliter of the sulfanilamide to the 50 milliliters of the standard. Just give it a mix. And we're going to let that sit for about 5 minutes before we add the NED reagent. So that time is up. Now we're ready to add the NED reagent. So again, it's 1 milliliter of the NED reagent to that same flask. Mix that in. And we have to leave this one now for 10 minutes for the color to develop. So 10 minutes have passed, and you should be able to see now in our flask this very faint light pink color. So that's the color of the azo compound we're looking for. And we should see, as the concentration of the nitrite in the standards increases, that the intensity of the color will increase as well. So just wanted to show you the highest concentration of standard. This is the 0.20 ppm, just so you can see the difference in the color. So this is the highest concentration of nitrites, and you can see we have a really bright pink color there. So the color for the other standards will vary from that light pink that we started with all the way up to the bright pink. So the concentration of nitrites will increase with the concentration of the color. So we're going to measure those on the spectrophotometer, and you will see how the absorbance changes with the intensity of color as well. Okay, so now that we have our standards all done for our calibration curve, we can move on to the samples. So we have two samples here, A and B, and they both contain an unknown amount of nitrites. So same as we did before, we're going to add the 1 ml of sulfanilamide to each one first. 1 ml to A, and 1 ml to B. And we're going to leave those for about 5 minutes before we add the NED reagent. Okay, so now we're ready to add the NED reagent. So 1 milliliter of NED to each sample. And again, we wait for 10 minutes for color development. Okay, so now we can see that we have a lot of color developed already in our samples, so A and B. So you can tell just by looking at them that there obviously is a difference in the nitrate concentration. One is significantly darker in color than the other. And you should see that reflected when we measure them on the spectrophotometer. So that's the next step. We're going to take our standards and our samples over to the spectrophotometer to get our absorbency measurements. Okay, so we're here at the spectrophotometer. And this is a UV-Vis spectrophotometer. So what that means is that it measures wavelengths in the UV and visible range of the spectrum. So if we look in the spectrophotometer here, you can see that this is where we put the sample. So the sample goes in a cuvette. So it's just a small square cell. We put the sample in there, and then that fits into the spectrophotometer. And it has to be oriented so that the glass sides, let's take that out again, you see that this cuvette has frosted sides and a clear glass side. So you want the light beam from the spectrophotometer to shine directly through those glass sides. So in this spectrophotometer, the light beam goes vertically through, so you want to have the glass side facing in that direction. So we're going to start by doing a blank. So we're just going to use some distilled water in our cuvette. Okay. I'm just going to wipe the outside of the cuvette with a wipe, just get any fingerprints or anything dirt that may be on it off. I'm just wiping the glass sides because that's where the light path shines through. So I'm going to put that in our spectrophotometer, close the cover, and we just press measure blank on the machine, and it will set it to 0. And then we can measure the rest of our standards. Okay, so we'll take that one out, we'll dump that, and we're going to start with our lowest standard. I always work from lowest to highest. Just fill up our cuvette. Again, I'm going to wipe off the outside. And I'm handling it by the frosted side so I don't get any fingerprints on it. We'll put it back in our spectrophotometer. And now it's giving us a reading for the absorbance for that lowest standard. So now we're going to do the rest of the standards. Okay, so we're just going to do the highest standard, again, so you can see the difference in the absorbance. So I've got that one filled up, ready to go, wiped it off, put it in our spectrophotometer, and you can see how the absorbance has changed, has increased with the increase in nitrate concentration. Okay, so now we're ready to measure our samples. So we'll start with sample A. Again, I'm going to fill up the cuvette. Wipe off the outside, put it in the spectrophotometer, and I still have it zeroed from when I did my blank previously. Should stabilize in just a second. Okay, so we have an absorbance for sample A. I'm going to move on. We'll take that one out. I'm going to use a clean cuvette for sample B. You don't need to go right to the top, as long as you have it almost filled, because the light shines through somewhere around the middle. That went in, so this is sample B, and measure the absorbance. So we would expect it to increase, because we could clearly see that there was an increase in the color intensity, and we can see that there is an increase on the scale. Okay, so now we're going to look at determining the nitrate content. So this is a rapid technique that is used for screening samples for the presence of organic matter. So it's a fairly simple technique. All we have to do is acidify the sample with hydrochloric acid, and then we can measure it on our spectrophotometer at 220 nanometers. Okay, so we're going to start with our standards again, like we did for the nitrites. So I have a series of nitrate standards. And again, we're going to start with the lowest one, the 0.1 ppm. Take 50 milliliters of the sample again, and that's already measured out here in this Erlenmeyer flask. So that's 50 milliliters of the 0.1 ppm solution. And to that, I'm going to add 1 milliliter of 1 molar hydrochloric acid. Okay. So now I'm going to do the same thing for all of the other standards, and then we will measure those on the spectrophotometer as well. Okay, so we're ready to measure these on the spectrophotometer, and you may notice that you don't see any color this time like you did the last time. And that's because the measurement for nitrates is in the UV range. So the nitrites was in the visible range, which means it's visible that we can actually see it, but in UV range we can't see it, but the spectrophotometer can. So we're going to start by measuring the 0.1 ppm, and then we'll do the 1.0 ppm. Now another thing for this technique is that we have to correct for the interference that may come from dissolved organic matter in the sample. So we're going to do that by measuring the absorbance at 275 nanometers, and if we get any readings at that wavelength, we're going to subtract twice that reading from the wavelength we get at 220 nanometers. So we'll do that first. We'll start at 275 nanometers. We'll start with the 0.1 ppm sample, and I've already measured a blank, so that's done. Okay. So it's set at 275 now. Okay. Give that a second, stabilize. So you can see we're getting a very low reading. So we may have some organic matter there. If you look at these samples, you can see that they look fairly clear, right? So these are just water samples. So we don't expect to see a high value for the absorbance at 275, but we want to check them anyway, so that's why we do that. So that's our 0.1. So we'll do the same thing for our 1.0. So measure this one at 275 as well. And again, low concentration, right? And low absorbance. Okay, so that's 275. So now we're going to change the wavelength on our machine, and we'll measure them at 220 nanometers. Okay, so I've changed the wavelength to 220 nanometers. Now I have my 0.1 ppm ready to go. I'll put that one in and measure the absorbance. So we see a much larger value than we got at the 275, right? So that's expected. So that's our 0.1 ppm. And now we'll do the 1 ppm. And you will be given the rest of the values for all the standards in between, so that you can use those for your report. Just showing you the lowest and the highest, so you can see how it works. So there's the 1.0 ppm. And again, we expect that to be much higher because it's 10 times the concentration. Okay. And now we're ready to do our samples. Okay, so now that we have our standards all measured, we can start with the samples. So we have two samples for nitrate, C and D. So I'm going to start with sample C. I already have it measured out into the cuvette. And again, we're going to do the same thing here where we measure at 275 and at 220 nanometers. So you can see at 275, we're getting a little bit of a higher value here than we got for the standards. And that's to be expected because sometimes in the samples, you would expect to have more organic matter than you get in a prepared standard solution that is made up with distilled water. So we'll record that for sample C. And now we'll do sample D. Wipe off the glass sides. So we're still at 275 nanometers. All right, so a little bit less interference from this one. So that's good. Okay. And now I'm going to change my absorbance on the spectrophotometer, change the wavelength to 220 nanometers. Okay, so that's at 220, and now we're going to measure the samples again. So sample C again. So fairly high concentration there. And finally, sample D. Get our concentration at 220. And remember, you're going to subtract twice the value you got at 275 from the value you get at 220 and use that to determine your concentration. And that concludes the nitrate portion of this lab. So one of the most commonly used methods for determining nitrogen content is a method called the Keldahl method. And it was developed in 1883 by a Danish scientist named Keldahl, so it was named after him. And even though it was developed in 1883, it's still really widely used today, as is one of the most reliable methods for determining nitrogen in food, in water, or in any sample really. So it's a three-step process that we're going to go through. It starts with the digestion. So right here we have a digestion block, and this heats up the sample to a really high temperature and digests the sample with sulfuric acid and a catalyst to break down the organic nitrogen into ammonia, and the ammonia reacts with the sulfuric acid and produces ammonium sulfate. So once that's done, that runs for about a half an hour or so, then we let the tubes cool down. This is a scrubber which cleans up any of the harmful vapors that are given off. I'll explain that in more detail later. So once the digestion is done, then we move over and we do a distillation. So we have another piece of equipment for that. So in the distillation, we add a strong base to it, so sodium hydroxide in this case, and it is a steam distillation that distills the ammonia from the sample into boric acid. So we put our sample in here. Inside this, the pieces you can't see, is a heating coil and a condenser, so the ammonia comes out into our receiving flask. And then the third and final step would be a titration, and we're going to use a digital titrator with hydrochloric acid to determine how much ammonia is in the sample. So we're going to start with our samples. So this is the digestion tube that we use to put our sample in, that we add the sulfuric acid and the catalyst to. It's basically just a large test tube. So we're going to start by measuring out our sample into the tube. So now we're ready to get our samples ready to digest. So here's our sample in the digestion tube. So we have a small amount of the water sample there in the bottom. And to that I'm going to add a catalyst tablet. So these are just little blue tablets, almost looks like a tongue. We'll put that in our sample. Two samples ready to go. Put one in each one. And then I'm going to add 20 milliliters of sulfuric acid. So this is concentrated sulfuric acid. So I'm wearing gloves because it's obviously very corrosive. I don't want to get it on my skin. So 20 milliliters of that. I'll go to my first tube. And then we are ready to add them to the digestion block. Okay, so now we're over here at our digestion block. So this is the digester, and you can see that our tubes with our samples in it have been placed into the heating block. So in here, underneath the samples, what the samples are sitting in, that's our heating mantle, and that will heat up to about 421 degrees Celsius, so very high temperature. On top of that, you'll notice this piece of apparatus, that's called a scrubber. And what that does is it takes care of any of the harmful fumes or vapors that are being given off when it starts to heat up. So remember, we put concentrated sulfuric acid in these tubes. So when the sulfuric acid heats up, it's going to give off a lot of vapors, and we don't want to be breathing that in. So the scrubber takes care of those vapors and neutralizes them before it releases it into the fume hood. So this is the part of the process where the proteins or the nitrogen in the sample is broken down into ammonium sulfate. Okay, so the protein in the presence of sulfuric acid under heat and with the catalyst produces ammonium sulfate. And then when that's finished, we will go on to do the next step, the neutralization and distillation. So we're going to let this heat up. You can see that it's only just starting to heat up now, so we put it on when it's cool and we let it heat up gradually, and then we'll let it run. Once it gets to 420 degrees, we will let it run for probably 20-30 minutes until the sample is completely digested. And you'll be able to see when it's digested because we'll see a color change in our test tubes. So see that when we come back. So our digestion block has been running now for about 30 minutes, and you can really see now those vapors that I mentioned. You see that the samples are giving out a lot of vapors. You can't really see the samples, you can see them a little bit. You'll see those better when I can take them out. So the scrubber is working now. Scroll over, you see it's bubbling away. So this works in that it has two solutions that the vapors are bubbled through. So we have a sodium hydroxide and then a water. And what that does is it neutralizes those acidic vapors that are being given off by the samples in the digestion block. So that's pretty much ready there now. So I'm just going to turn it off. We're going to let it cool down and we'll be back shortly. So our samples have sufficiently cooled down. They're all digested. So now what we are going to do is add 75 milliliters of water to each one, just to dilute it before we do the distillation. So I'm just adding water, and I'm doing it carefully because we're adding water to acid. So we tend to get some vapors given off when we do that, which you can see there. So we're still working in the fume hood as well. So we add 75 milliliters of water. And now you can really see that bluish green color. So that's the color we would expect to see. So now that those are all done, we're going to go ahead and start our distillation. So now that our samples are digested and cooled down, we're ready to start the distillation. So this is an automatic distillation unit. And inside this machine, what you can't see, there is a heating coil which heats water to produce steam, and a condenser as well. So we heat the sample, which liberates the ammonia, and then it is distilled by steam for about 5 to 7 minutes through a condenser, and then the ammonia is collected in the receiving flask. So when we put our sample on, so our sample tube fits in here. And this tube that you see in the middle is the tube that supplies the steam. Make sure that's in there nice and secure. It has a safety door so that if there's any splashing of alkali or anything, it stays contained within the apparatus. This is our receiving flask, and in this flask is 25 milliliters of boric acid, and it also contains an indicator. So there's an indicator in there that will change color when the end point of our reaction is reached. So this is an automatic titrator. Once we have our sample and our receiving flask in, we can press start. And you should see fairly soon here now the alkali being dispensed into the tube. So the alkali in this case is sodium hydroxide. There you go. So that's dispensed in the tube. And you can see that that's a fairly vigorous reaction because it's a concentrated base reacting with a concentrated acid. Remember the sulfuric acid that's in our tube. And once all the alkali is in, the steam distillation starts. So you can see the bubbles being produced there in the tube. So that's being pumped into the sample tube through the steam tube. And that will run now for about 5 to 7 minutes until all of our ammonia is collected in the receiving flask. Okay, so our distillation is complete, and you can see that this machine automatically drains our tube and dispenses that into waste. Our receiving flask you can take out, and you can see now that it has changed color, so it's a greenish color as opposed to the red we had when we started. So that means that our ammonia has been condensed into the receiving flask, and now we're going to perform a titration with this solution. So just so you can see the difference in the color, the flask on the right is the original color of the boric acid with the indicator before the titration, and now we can see we have this greenish blue color of the solution after the titration. And the color change is due to the ammonia that was liberated from the sample reacts with the boric acid to produce ammonium borate, and that's what produces a color change. So now we're going to titrate this with a solution of hydrochloric acid. So we're using a digital titrator, okay, rather than a burette. And we're going to titrate that with hydrochloric acid, and the volume of the titrate that we use is the value that we'll use in our calculations to determine the amount of nitrogen in the sample. Okay, so let's start the titration. So I'm just adding hydrochloric acid very slowly at first, and we're looking for a color change from the green color to the original red color of the boric acid with the indicator. Okay, there we go. So you can see we're right back to that original color that we started with of the boric acid. So we've reached the end point of our titration. So that volume that we added to this flask, that's the volume of the titrate that you're going to use in your calculations. So it's the volume of the hydrochloric acid that we had to add to reach the end point. So now I'm going to run the rest of the samples plus a blank, and you will be provided with all of that data to use in your calculations. Thanks for watching. I'll see you in the next lab.